Okay, so good morning, everybody, and good afternoon, depending on which part of the world you are in. And it's a pleasure today to have Professor Kulik, who will be talking to us about DFT+U and some of her work, like DFT+U plus V and things related to this. So she'll be talking about DFT and DFT+U. So Professor Kulik got her PhD in 2009 from MIT. And since then, she has won many awards, including the Journal of Physical Chemistry and Physics Division Lecturership Award in 2019, the NSF Career Award 2019, Marion Milligan Mason Award 2019, the DAPA Young Faculty Award, the ONR, that's Office of National Research, Young Investigator Award in 2018, and the ACS OpenAI Outstanding Junior Faculty Award in 2018 also. Her research interests are in catalysis, transition metal chemistry, electronic structure methods, atomistic simulations, enzyme catalysis, and of course, the one that is probably her most famous, the work for which she's most known for is her contributions to DFT+U. I actually first came across her work in a few years ago when I was working with one of my students, Bruno. We were trying to learn about DFT+U. And then we came across these fantastic tutorials online that were made by Professor Kulik. Actually, if you are beginning to learn DFT+U, I'll say look online. Just make an internet search for Kulik and DFT+U. This very good tutorials website will come up that you can learn a lot from DFT+U. So she'll be talking to us about DFT+U and beyond today. Thank you very much, Prof. Kulik.
Thanks for the kind introduction and for the invitation to speak. So I will go ahead and get started. And as I mentioned, if it's the preferred style to interrupt, that's absolutely fine. I've also tried to put in some newer work my group has done that's theoretical and kind of related to some of the concerns with what we think about when we think about DFT+U. But depending on the audience, it might be a little bit too much content, so I'm happy to stop a little early. And then I also thought I would waste some of my time by telling an anecdote that actually the reason I started those tutorials was because when I was a postdoc, I went to visit Lawrence Livermore National Lab. And I went to see a very famous physicist in the field, and he said, I read your papers, but I didn't understand anything in them. And I thought, okay, if other PhD scientists, so I was a young postdoc, if other PhD scientists don't understand what it is that I'm writing in my papers, I need to do more to make them more accessible. So that was the motivation for the tutorials. And I will go through some of the work we've done since. We've moved into a lot of different areas in my independent career and trying to understand DFT+U from different angles. And so I will go ahead and talk about some of that today as well, but I'll start my talk with some basics and history of DFT+U. Okay, so one of the reasons we in the physics community like DFT+U is because it can be connected transparently to this idea of the Hubbard Model, which is something that many people learn in undergrad or grad school, which is the idea that when we're describing phases of matter, balancing between how a metal works and how an insulator works, we can describe this as the interplay in a simple model Hamiltonian between how much energy it takes to hop between different sites. So how freely can electrons move between different sites versus how much do they like to localize onto the site. So do the electrons like to be well localized? A chemist might describe this as a localization challenge, or are electrons sitting in isolated atomic-like orbitals, or are they free and delocalized throughout the material? The Hubbard U then in this context is the difference in the energy of ionizing an electron from a specific subshell, typically the D subshell. So NL here is the principal quantum number in angular momentum. That would be 3D in many cases, or 4F for some of you working on F electron systems. And I here is the site, or the atom I. And so the Hubbard U then is the difference in energy that it costs to ionize an electron from that site versus to gain an electron for that site. And that can be recognized as a finite difference of the curvature of the energy with respect to occupations. So this is simply something related to a chemical hardness problem that chemists might talk about, but is something fundamental that, for instance, you can look up in atomic tables of electronic properties of atoms. Now, people traditionally don't do that. People instead typically talk about computing the Hubbard U, because if you were to get this ionization potential and electron affinity of the subshell directly from the atoms, it lacks the screening that's inherent in the solid state material. So if you go back into the early Hubbard papers, what he thought the value of Hubbard U would be is actually far, far in excess of what the appropriate value is in a solid because of the screening effect. And specifically, I'd like to point out that this is for the subshell. So this is the ionization potential and electron affinity of a particular subshell, which most of the time we're talking about the orbitals that are well localized, but I'll get into that in the next slide. I'm getting ahead of myself. So again, this is a finite difference approximation to the second derivative of the energy with respect to variation of the on-site occupations. And that's something I'd like to go into a little more detail about. And as a result of this, you can view this as a type of chemical potential of the D subshell with respect to the rest of the system. And this will be important as we talk about Hubbard U. But in one slide, roughly, I'd like to go through the full history of Hubbard U, and I'd like to point out that everything for DFT+U, this perspective I wrote now, I guess about 5 years ago, in Journal of Chemical Physics, I think covers well everything that's on the slide, but I'll go through it in one slide, which is, yes, from the Hubbard model, we recognize the importance of a metal to insulator transition. And it turned out that in the early days of the local density approximation, so in the 70s, where the generalized gradient approximations many of you probably used didn't even exist yet, DFT was in its infancy and wasn't being used in chemistry at all, but was being used, for instance, with the LMTO, the muffin tin approximation. It was being used in very approximate ways in early computers. It was determined that you could actually use DFT to compute these Hubbard U values. And this worked pretty well. But then it failed pretty dramatically. So people were using the Hubbard model. LDA+U didn't exist yet, but people used the LDA to compute Hubbard U's in the sense of what should go into my Hubbard model. But this would fail catastrophically if the ground state you were trying to compute Hubbard U from was wrong. For example, if you were trying to compute Hubbard U for an insulator, but the LDA calculation produced a metal. And the first suggestion that self-interaction correction was what was missing from the LDA in order to accurately compute Hubbard U's, roughly speaking, is in this 1988 paper that many people don't cite too much. But basically it points out that there's a problem with the LDA for extracting Hubbard U parameters when the ground state is wrong. And that is when the two worlds collided. So DFT was just a mean field theory that could be used to compute Hubbard U's that would go into Hubbard model Hamiltonian calculations. Then it was introduced in 1991, the idea that maybe we can just directly add the Hubbard model Hamiltonian, subtract out a double counting term, and use that to correct the metal to insulator, to induce a metal to insulator transition inside the LDA to turn the ground state computed with the LDA into the correct ground state. And then in theory, that could be used to extract Hubbard model parameters and so on, but things obviously took a pretty dramatic turn. Some of the questions in this method are, to what extent, in what form did the double counting term take? And the most widely used double counting term is this one from the 1994 paper, which is the fully localized limit double counting term. And so the double counting term aims to take into account everything that's in the DFT functional already, that when we go ahead and add the Hubbard correction, we don't want both of these. You should keep in mind that the double counting term is always a measure of empiricism. There always has to be some approximation for how we're going to treat this double counting term. But then I guess the key thing here is the Dudarev et al. Approximation from 1998, which made a further simplification. And I'll talk more about what typical functional forms look like for the rest of my talk. This is more of a historical slide. But this is the standard DFT+U with a J term included. And the J term can be thought of as a measure of exchange. It measures some correction, so it treats same spin and opposite spin electrons differently, just like quantum mechanical exchange does. But what Dudarev showed was that you could simplify this expression by neglecting this term, and this is often called U effective equals U minus J. The key thing to note, and this is discussed in the 2015 JChem Phys, is that if you have two states being compared, the J term will just modulate the U. But if you have three states being compared, so for instance, you're trying to compare three phases of matter or three different intermediates, the difference of U and J will matter much more. So this is an approximation. It doesn't make the physics better, but it recovered rotational invariance and greatly simplified the form of DFT+U. And it also made transparent the relationship between DFT+U and not just the Hubbard model, but well-known errors in density functional theory. And so if I don't go too slowly, I will get to some discussion that has been really close to my heart in trying to understand how does DFT+U actually get us closer to the right answer for the right reason in approximate density functional theory. So the simplified form of DFT+U, especially if you use quantum espresso, that many people are familiar with, is the one that neglects the J terms, and I will bring back J in the second half of my talk, but just as a reminder, the occupation matrices here, that's a bolded N, consist of occupation matrix elements, which take our extended states and then project them onto a localized set of atomic orbitals. And that tells us what the occupations are in our DFT+U calculation. And so these atomic orbitals, phi, come from typically from the pseudopotential generated, so they can be sensitive to the pseudopotential you pull off of the website. Some of this is discussed in the appendix of some of our papers, as well as some discussion in some papers by the Payne group. But we need to take our extended states and understand how localized or not are our electrons, and the occupation matrix is the key ingredient for that. And then the other thing to note is that if you take the first derivative of the DFT+U energy with respect to occupations, it is positive for the potential shift is positive for less than half-filled orbitals and negative for more than half-filled orbitals. And it approaches zero for exactly half-filled orbitals. And so what this means is that DFT+U in practice will penalize fractional occupations by emptying partially filled, slightly filled orbitals and filling mostly filled orbitals. And this happens to counteract a lot of key issues in approximate density functional theory. For instance, going back to the Purdue, Parr, Levy, Valdez paper from the 1980s, we know that the exact energy functional, so density functional theory or any other method, should be piecewise linear with the addition of an electron. And that addition of an electron should get less and less favorable, so it should follow the form I'm showing here on the left. We know in practice that approximate DFT functionals, LDA or GGA, lack that derivative discontinuity, and so they're smoothly varying. And they tend to have minima close to fractional occupation. So the curve is convex. It curves below where this exact piecewise linearity is. And it was suggested that if you take a look at the functional form of DFT+U, and especially in its simplified form with the J neglected, you can see that it is 0 at integer occupations, and it curves upwards in a parabola between those two limits. So it looks something like this. And you can convince yourself that if you add the red and the blue curve together, you should be able to recover the exact behavior. So I will talk in a few minutes about whether or not that really holds, but that's the motivation from an electronic structure perspective for why DFT+U is appealing as a fundamental approach to recover improved predictions from DFT without incurring the cost, especially in the solid state, of a hybrid functional. So this is about my only slide about how to calculate Hubbard U, so I'll try to go a little slowly. Linear response Hubbard U was first introduced by Warren Pickett in the 1990s, but was popularized by Matteo Coccaccioni and Stefano Di Giaroncoli in their 2005 paper. And the basic idea is we need some way to understand what is the second derivative of the energy with respect to varying the d electron occupations if we want to know the Hubbard U of the d shell. But to do that is pretty hard. You would normally need to do constrained DFT. So what linear response U does is instead is it applies a rigid potential shift alpha to the d states with a term alpha n. So it's just rigidly shifting anything that has a matrix element in that occupation matrix. And then in doing so, it can be shown that that's directly related to the Hubbard U. And so what we want to do is we want to get that response property. So we apply different potential shifts alpha. We do a linear fit. All of this is detailed on the website. We subtract out what's called the bare shift. And we compute the self-consistent shift. And so we look at how the D occupations change if we empty or fill these levels. And so in doing so, we can compute a linear response Hubbard U. Now, a natural question might be, if the ground state I'm computing the Hubbard U on isn't the ground state I'm going to be in with DFT+U, what should I do? And you can do that in what's called the self-consistent U. This is from my first paper from my PhD, which is simply to say slowly increase the Hubbard U, then recompute the linear response U, and you can show that there's a simple relationship that extrapolating back at higher U values to UN equals 0, so that's where you've applied no UN, can get you the self-consistent U. In many cases, the self-consistent U evaluated on the DFT+U density and the linear response U evaluated at the PBE density are almost identical if the states are qualitatively the same. It's only when you say have an LDA or PBE metal that you actually want to calculate the Hubbard U as an insulator that you need to apply the self-consistent scheme. And so I will talk in more detail about what computing the linear response U can do for you. Many people use the U as a tuning parameter regardless of the fact that they could compute the linear response U fairly straightforwardly. And I'll show reasons why you might want to do that, why you might want to just treat it as a heuristic parameter, or why you might want to compute it for most of the rest of my talk. But one of the things that always attracted me to computing the linear response U is that it's fundamentally a property of your system. So what I'm showing here is a series of what are called isoelectronic diatomic molecules. And the Hubbard U conveys information about how the d orbitals, or whatever subshell you're computing Hubbard U on, how those d orbitals are hybridizing with the rest of the system. So for instance, when we compute the linear response U in this way of increasingly ionic molecules where the bond goes from more covalent and delocalized to more ionic, the Hubbard U that we compute intuitively follows this trend that it decreases. And it decreases in a way that makes sense as the bond gets more and more ionic. So Hubbard U values are generally going to be high. The more covalently bound our system is, the more delocalized the electrons are. And this is something we could compute anyway. What we're trying to do is we're trying to get the second derivative of the energy with respect to variation of occupations. And the reason we do linear response U is that it gives us an easier way to get at that property, which again is recomputing the occupations when we shift how high or low those occupations are. That's what's being shown schematically. So again, I mentioned that one of the more useful things about DFT+U is just to be practical about what it can do for you. And I would say one of the things I love most about DFT+U is that it's so simple when you actually look at the analytical form that you realize there's only so many things it can do. If DFT+U doesn't make your prediction better, it's very easy to troubleshoot why that might be. And what you can do is you can say, especially in the simplified form, all we're doing is imparting a relative energy penalty based on occupations. So if we have two energies we're trying to compare, or something's not the ground state and we want it to be the ground state, if we can tune its energy by the occupation matrix, and we can compare two states by how different they are based on the occupation matrix, then doing so is a way that we can use the Hubbard U essentially as a tuning parameter to shift the energies to where they need to be. And it makes sense that this works generally in LDA or PBE calculations, because LDA and PBE through self-interaction error do in fact have a tendency to overfavor and overstabilize things with more delocalized, or as we call it in this paper, fractional occupations. So some examples of this are that when you compare spin states of molecules on surfaces or in isolation, this is a tetrabromophenylporphyrin with a cobalt center on copper 111 that we studied over the years. The occupation matrix elements, I'm showing here the eigenvalues of the occupation matrix, which tells you something about basically how fractional it is, and these are lit up red when they're more fractional. Basically, you can see that the high spin state is less fractional. The occupation matrix penalty is going to be smaller for the high spin state than the low spin state. And for instance, low spin states tend to be overstabilized in PBE. So applying a Hubbard U should push up in energy the low spin states, down in energy the high spin states, and should generally correct a bias we know we have in LDA or PBE for non-magnetic systems over magnetic systems. It turns out if you take this very practical approach, you can apply this to other things like thinking about correcting relative energies of organic molecules. We did this in this 2016 paper. And you can also, this is not actually the correction itself, but this is the Hubbard U calculation of different platinum atoms on the surface of the carbon monoxide on platinum 111 problem. And what you can see is that the Hubbard U is a very sensitive reporter for differences in the local occupation matrix and hybridization for different adsorption sites. What you see here is that the Hubbard U is highest for the cases where the carbon monoxide is bound. This doesn't mean that DFT+U will definitely fix this problem. There are many ways people have looked at fixing this problem, but you can see that the computed linear response U or the occupation matrix reports differences in the hybridization. If this is exactly the way that we want to correct the relative energies of these sites, then we can choose a Hubbard U that differentially penalizes these sites. Now, challenges for this in surface science, yes?
Sorry, are you using different U's for different atoms of the same type?
So you can. Here, the one on the right is simply showing linear response U calculations, not which ones are correcting. I will show a surface science application in maybe it's the next slide, actually. I should remember that, where that might be motivated, but absolutely that one could do that. It naturally introduces some practical challenges of doing it.
Okay, thanks.
But this for sure, I would say this linear response U map for sure motivates the idea that if you were trying to implement the linear response U, you would want to use different U's on different sites. And when I would say you would want to do that is if the computed U values differ by at least 1 eV from a practical perspective. Okay, so this was not, maybe I'll skip through this pretty fast. I will skip these next two slides because I'm running a little low and I think this is less important to the audience. But one of the reasons I got into Hubbard U, or why we stuck with it over, say, hybrid functionals, and a lot of my PhD was focused on molecules, was that there were key challenges, very simple, seemingly simple challenges where getting the right electronic state ordering was really hard. And one of these was the iron dimer. From experiments, people had deduced that all of the electronic structure calculations at the time done on the iron dimer were incorrect. because you could get all this information from spectroscopy that basically the two lowest lying states of the neutral iron dimer had the same structure, and they were both more tightly bound than the iron dimer anion, and they knew roughly what the bond length should be, so they deduced certain term symbols and electron configurations that these should be D13 with a difference of the 4s electron pairing. And so you would think something like B3-LIP might do a good job of this, but it turned out that to get the states correct and to get their energy gap correct with respect to experiment, you get this exactly right with a self-consistent DFT+U or with high-level correlated wave function theory, but you get a number of things were very wrong with PBE, but also still wrong with DFT, with hybrid DFT. So this is sort of what I worked on in my PhD and early on, but I wanted to get back to the question of the interplay of different types of errors for the rest of my talk and tell you a little bit more about more modern interpretations of DFT+U. This was just a motivation for that DFT+U can do helpful things, but you have to be aware of, and this will be a theme throughout the rest of my slides, DFT+U is only going to work if the occupation matrix differentiates the different states. In the case of the iron dimer, differences in hybridization, basically there was too much delocalization in this lowest maroon state, and so DFT+U pushes it way up in energy into the correct spot with respect to experiment or high-level wave function theory calculations because of differences in the occupation matrix. So I want to get back to this question of different fundamental errors in density functional theory for the second half of my talk. And I like to think of it as this unpacking of a box of many different types of errors that can arise in our underlying exchange correlation functional. And I try to decompose them, but what you usually find, and you've seen this in the literature, is that improving one of these errors tends to worsen another. So the question is, with DFT+U, and what I'd like to highlight is, are we always improving one error at the cost of another? And so energetic delocalization error used to be called self-interaction error, but it's that convexity I've talked about. That will be a big theme in this talk. And that's how much we deviate from this exact piecewise linearity. Density delocalization error. So we often talk about DFT+U as penalizing delocalization of the density. So how much does that factor in, and how closely related is that to what I'll differentiate as the energetic delocalization error? And then static correlation error, this has not been as widely discussed in the context of DFT+U, but should be and will be the focus of some of the work I'll show you, which is that if we localize electrons too much, things like Hartree-Fock can actually unphysically penalize breaking of bonds, and that's why we never use Hartree-Fock to study metals. And then finally, if we were to eliminate density errors, energetic delocalization error, static correlation error, and we're still left with errors with respect to experiment, I just call those relative energy errors. So what errors remain when we've corrected all of these fundamental errors with respect to matching experiment? I'd like to just highlight the relationship between energetic delocalization error and static correlation error, because I think it's important to understand that when we're doing standard DFT+U, we're fixing this thing on the left at the cost of worsening the thing on the right. And most problems people run into in DFT+U are that this problem on the right starts to rear its head and be a big challenge.
Sorry, for band gaps, which of these two errors are more important?
So for band gaps, the lack of the band gap arises from the left. But if we're interested in, say, properties like a bond dissociation energy from an insulating material, then the property on the right, for instance, starts to make a big difference. And then when we want no band gap at all for systems with strong static correlation error, then we then fixing the thing on the left makes the thing on the right so bad that we get the electronic properties, say the band shapes, wrong due to the static correlation error.
Okay, thanks.
So, so something that we had worked on that is I think a fundamental question that basically the too long didn't read on this is Use the Hubbard U you want to use and don't feel obligated to compute the linear response U, but that's not what I would have told you 10 years ago. And so I'd like to tell you a short story about this question of what is the real relationship with recovering this piecewise linearity. So I had just told you that if we know how to use the right Hubbard U, then we should recover piecewise linearity. And this should be true if when we add or remove an electron to our total system, this shows up in our occupation matrix. So if I add an electron to a molecule or a solid and it goes exactly onto that D subshell and it shows up in my occupation matrix, then U n times 1 minus n will exactly correct this. But when we're computing Hubbard U, we're computing a curvature of the energy where each point at the bottom is a stationary point. So we have a self-consistent solution and then we're pushing away from that self-consistent solution by moving occupations off of, say, a metal center to the rest of the system at constant charge. So I just a few years ago wanted to know what is the relationship between the local, what I'm going to call the local curvature, which is the linear response U we just learned how to compute, and what has been popularized in the literature, say from Baer, Kronig, Auschbach, and others in computing optimally tuned range separated hybrids is this concept of global curvature, which is known to be roughly what is the mismatch in the HOMO and the LUMO. But basically, the global curvature is this blue curve. So what is the second derivative of this blue curve, and how does it relate to the second derivative of the red curve? And those are not the same quantities. You might expect they should be proportional, but in one case, what we're doing is we're moving electrons off of the metal center to somewhere else in the molecule versus are we adding or removing electrons entirely? And the focus of optimally tuned range separated hybrids has been to say, let's correct the error in adding or removing electrons from the whole molecule, whereas the focus of the Hubbard U community and DFT+U community is let's correct this local behavior of the metal. And so I just wanted to know, are they the same or are they different? And in turn, even though I've shown you a few schematics, can we correct the lack of piecewise linearity in a DFT functional with the Hubbard U term? And so we did this a couple ways. I'd say the key things to note are that we use Martina Tuckerman's scheme to enable comparison of energies at different charges. We do this on molecules that are isolated, and so we just neutralize the cell boundaries. And we carry out explicit fractional charge calculations. So we actually add a fraction of an electron to the whole system and then look at what the energy does. And the spin state of these systems is high spin if I don't otherwise specify it. There's also a nice spline expression, so you can look at this without explicitly calculating fractional charges. That's what's done up here. This was introduced by Aaron Johnson. And so in short, either the fractional charge explicit calculations or the spline shows that DFT+U, in fact, what we should want to see is a completely flat line here if we have piecewise linearity. This is just the deviation from piecewise linearity. And starting from PBE, if we incorporate a U term, we actually incorporate a U term and somewhere around a U of 5 in the system, what happens is we actually recover piecewise linearity. So DFT+U is doing exactly what we had said all those years ago it should do. It actually is fundamentally getting us closer to a condition that we say the exact functional should recover, which is that it should be piecewise, the energy should be piecewise linear. It does other things that are helpful. So for instance, the question before was about band gaps. We know in practice band gaps are underestimated because functionals lack the derivative discontinuity of the exact functional. So for GGA, as we fill an orbital, its eigenvalue shifts up linearly until it hits, so here would be the HOMO of the n-1 electron system. This would be the HOMO of the n electron system. And the exact should be stepwise. That's what's called the derivative discontinuity. These are the eigenvalues. This is what a GGA will do. And in fact, when we do Hubbard U on the system and we add electrons, we actually start recovering that derivative discontinuity for similar reasons. So even with a small amount of U, but ultimately at the same U that recovered, this is essentially redundant information, but the same U that recovered piecewise linearity, we also recover this desired shape of the derivative discontinuity of the step. And as a result, that's why a DFT+U approach improves band gaps. So this is a delocalization error problem that fixes band gaps. Now, is the electronic structure good of the open gap system? Are the states themselves good? That's more of a static correlation error question. And so I will skip past this because I'm going a little slow, but we went through, because I mentioned one of my favorite things about DFT+U is that it can only do so much and you can understand everything it can do. You can actually use the spline expression to derive, will DFT+U ever make things worse? Will it ever take us further away from these exact conditions? Will it ever take us further from piecewise linearity and make the delocalization error worse? And the answer is no. But the most it can ever fix these deviations or these errors is about 1/8 of an electron volt per electron volt of U. So if you have a certain amount of error in your PBE system, you're going to fix it at a maximum rate of 1/8 of an electron volt of error. And these errors in molecules, for instance, are quite large. These errors are easily work out to that your Hubbard U in this way should be about 8 eV. So the one I showed you was a little bit cherry-picked. The right answer to recover this piecewise linearity was about 5. That's probably what a lot of people use in practice if they're just using a heuristic U. But you can work out that because the errors in PBE are so significant that the Hubbard U you need to recover piecewise linearity could easily be around 8 eV or more. And so I think I will take a brief segue here to something that might be more relevant to the audience at hand. And then I will get back to some of the questions regarding this. But whether or not this curvature interpretation of Hubbard U is useful for thinking about improving properties. But one key common failure of DFT+U in the solid state is that sometimes it doesn't always do anything or do what we want it to do. And for instance, an interesting challenge is that in catalysis, surface formation energies in something like PBE tend to be too stable. That has motivated surface-dependent functionals like PBE, Sol, and so on. But ironically, the surfaces are too stable, but they're too reactive. And when I teach catalysis in chemical engineering, usually I say if a surface is unstable, then it's more reactive. So it's weird that, and this is known for metals, there was a Nature Materials paper about 8 years ago describing this as in the context of the Platinum 111 challenge, but here I'm looking at transition metal dioxides for water splitting. And what's interesting is I'm showing here hybrid tuning, and this is the sensitivity versus DFT+U tuning, and what you can conclude is for early to late transition metal dioxides, DFT+U will correct some of the surface energies in the early transition metals, but it fails to correct it. The bars are way too short in the later transition metals. And then if you look at adsorption energies, DFT+U will shift the PBE adsorption energies in the late transition metals, but not in the early transition metals. And this turns out to occur because when you look at the occupation matrix differences between the bulk system and the surface system, or the adsorbate and without the adsorbate, for early transition metals, the early transition metals, the DFT+U with atomic occupations detects very well the surface that you've gone from a bulk system to a surface. But it doesn't detect very well that an adsorbate is present. The adsorbate doesn't light up like we saw in the case of the platinum. But you can see for platinum over here, putting the adsorbate on that particular atom, the occupation matrix shifts a lot. Whereas for the surface, it shifts very little. And so the result is, for instance, our recommendation for something like these rutile transition metal dioxides is that you can't actually, with a standard formulation of DFT+U, shift both the surface energy and the absorption energy, because the occupation matrix can only detect one at a time. Whereas something like a hybrid, either a local range separated hybrid like HSC, which is not too expensive, does a much better job of recovering the reference energy. You can see here universally PBE starts in the wrong space. And that's the white circle in these two plots, and applying hybrid tuning, unlike DFT+U, can shift us in the right direction towards the reference, both increasing the surface energy and increasing the absorption energy. So destabilizing the absorption energy. So this is something to think about. DFT+U cannot fix everything, and there are limitations on what it can do. But in the cases where it does work, it has this theoretical maximum of doing things the right way. And in order to have that positive effect on your electronic structure, what you need from DFT+U is you need the occupation matrix to detect the difference in the states you're wanting to penalize. So you want to see this greater fractional occupation on the sites that you're intending to penalize. When the occupation matrix can't see that, which is the case, for instance, in this titanium problem for the absorption energy, or this platinum problem for the surface energy, then DFT+U has no effect. So that's one thing to say, is for the most part, in the best worlds, DFT+U can fix our electronic structure problem from PBE or LDA. In the worst case scenario, it frequently does nothing. There's some third class of categories where you can have other problems, but those are the two I'm going to talk about today. So that was an aside, but I think coming back to a more fundamental question, and I'll talk a little bit about the static correlation error also in the next couple of slides, is that when we got into this question of recovering piecewise linearity with the global curvature versus Hubbard U, I thought these two would be proportional. If you're removing an electron from the overall system and it's coming from the d orbital versus you're removing it from the d orbital to the rest of the system, I thought they should basically be proportional, because I'd spent my entire PhD saying, compute the linear response U, and there's this big community of people who focus on recovering piecewise linearity through optimally tuned range separate hybrids, and they've been showing they get better properties that way, especially in organic molecules and spectroscopy and so on. And this is what we saw. So on the left here, global curvature is the Stein-Kronig expression. It's based on the deviation from piecewise linearity. And this is the linear response Hubbard U on the x-axis. And you can see they have the opposite of a positive correlation. They have a very strong negative correlation with a slope close to -1. We showed in this paper that all sorts of materials have this relationship. So what this is telling us is something a little bit troubling from a fundamental perspective, which is that as we go from weak field ligands, water weakly coordinates our metal, to carbonyl, which strongly coordinates our metal, the global curvature decreases. So this is known that global curvature is not size consistent. And so basically the molecule with carbonyl ligands looks bigger. The Hubbard U, I told you, increases when we have more delocalization in our system. So you're kind of left with a conclusion, or at least I was at the end of this work, is that neither of these are really fully satisfactory in understanding what is wrong with our DFT functional. So either the deviation from piecewise linearity, basically the bigger our molecule gets, the smaller that deviation will appear to be, but the Hubbard U will not decrease. So the Hubbard U is satisfactory there, but if we use this Hubbard U only in cases where we're close to this parity line, will we actually exactly recover piecewise linearity. So we'll often leave behind a little bit of residual delocalization error. And after I got sad a little bit that my thesis had just been refuted, I realized that this actually makes sense. So this is what we're doing when we're doing Hubbard U. We're again moving from a stationary point at constant charge and moving occupations. And whereas when we're computing the global curvature, again, remember, we're looking at this energy that shifts as we add the total charge. Where does it go? And you can very quickly work through the math that these two curvatures should not necessarily ever be the same. So that's a more fundamental point, and I'd like to finish with, I know I've covered a lot. I'd like to finish with this another way of thinking about DFT+U in the context of the flat plane. And this is something popularized by Wei Tao Yang and coworkers, is this concept of the flat plane, which is that, and I think it's important that I show this, but if I don't get through all of this, I think that's fine in the next few minutes. The key things to note here, if this looks unfamiliar, is that the edge in the front is the same piecewise linearity condition that motivated us to use DFT+U, but the flat plane is the union of a second constraint, which says that when we take an isoenergetic orbital and we flip the spin from up to down, or even split half spin up and down, those should all be the same energy. And that, it turns out, is something that is held true in LDAs that I will show in a minute we give up when we do DFT+U, but the flat plane condition is the union of those two constraints across. So it just is a complicated looking thing that's basically the piecewise linearity condition, but with a second condition. So this creates the flat plane condition. And what's helpful is for ions, as I mentioned, you can look up IP and EA from a table, so you can actually construct exact experimental flat planes, and you can know exactly what the right answer should be across all of these different combinations, where each point in this plane is a combination of spin up and spin down electron occupations. And so the key thing, if you're not used to thinking about the flat plane, is that everything that improves electron delocalization error worsens static correlation error. So this is what I was mentioning before. This is from work of Yoke and Ouchbach on some ytterbium complexes. And so things like the optimally tuned range separated hybrid or the global hybrids all increase the static correlation error, which we're now showing as a parabola that goes this way. But PBE had very little of this error to start with in comparison. And so by construction, you can work out that the functional form of DFT+U, when we recover piecewise linearity, so when we eliminate the EDE, we're proportionately dramatically worsening the static correlation error. So that's something important to know. If static correlation error matters in your system, standard DFT+U is going to make everything worse. And this can lead to things like, say, small low-lying states you may have encountered that, depending on how you set up your DFT+U calculation, the electronic structure converges slightly differently, and the energies can be dramatically different. That's a hallmark of static correlation error. And so everything like a global hybrid or DFT+U, what it does is it essentially puts a bowl on the flat plane. It fixes the edges, but it takes the middle part of the plane that wasn't bad in the first place and it makes it worse. So what we wanted to do instead was we wanted to say, well, how do we recover exactly, forget DFT+U for a moment, how do we recover exactly the flat plane condition? And so we first called this Jello mold DFT because we wanted to take a mold of the shape of the flat plane errors and reconstruct that flat plane exactly. Now, the reviewers said, you can't call it Jello mold DFT, no one will take it seriously, so we called it judiciously modified DFT, which has the same acronym, JMDFT. But in any case, this is what a PBE flat plane looks like. It's too smooth, but it's very flat in the middle. The exact solution should look like this. And when we take the difference, you can see why this bowl-shaped thing doesn't work, is that we're fixing the edges where we had the energy being too low, but we actually already have, even in PBE, the energy being too high along this other part. And this shape is generally universal. So how did we work with judiciously modified DFT? Well, we started by just looking at, can we get back to DFT+U in a low coefficient form and find a way to improve DFT+U to actually recover the flat plane and not make the middle parts worse. And so I'm skipping over some of the details of this, but we'd like, just like with Hubbard U, we'd like a way to non-empirically extract coefficients and then recover not just the delocalization error, but this other condition for static correlation error as well. And so what we did was we just inverted the errors and looked at how we could correct them. And we did all of this in quantum espresso, and we looked at whether we could add back the J term. And it turns out that U or U with J cannot reduce the errors on this flat plane. There's no way to tune any amount of coefficients to eliminate these errors. But we looked at other ways of doing this. We added other terms, and it turns out that once you start to add a little more flexibility to your functional form, and we call the one that we went with U, J, and J prime, it just adjusts the definition of J depending on which part of the flat plane you're on, you can actually eliminate almost all the errors in here. And this is dramatically reduced with respect to PBE. But you cannot do that with just a standard U and J alone. So what we went with was this U, J, and J prime, and the result is that we could eliminate the errors. This is the PBE error along the fractional spin line. This black line here is the exact solution, and this JM-DFT approach, which is a slightly modified DFT+U, can recover the fractional spin line. We also, in case you think I'm just zoomed out, we also recover the delocalization error, which is what we showed we could do with the standard DFT+U. And we actually, I think I am coming up on finishing on time because I went through this really fast. We actually later showed that you do know the non-empirical coefficients for this. They're not the linear response Hubbard U, but in the case of the U's that you should use to recover the flat plane, they're the global curvature. So that's the right way to recover at least this exact condition. And that's been known for some time. But then what we also did was we derived coefficients for the J terms, the J and the J prime, and those are related to how much the eigenvalues are mismatched. So if you ever run a calculation with spin polarization and your spin up orbital of the same shape as your spin down orbital have different eigenvalues, they're mismatched. You've probably seen that before. That's a hallmark of static correlation error, and that can give rise to errors in bond dissociation energies as well as electronic properties and so on. And that's why DFT+U can fail in cases where maybe an LDA or PBE would be superior. So this approach specifically corrects both of those types of errors at the same time. And the non-empirical coefficients generally, they're not from like a linear response Hubbard U formalism, but they are from the electronic structure of PBE. They're from the eigenvalues, as I just showed. And because the fit U and J, just to recover the errors, and the non-empirical U and J match, we generally are able to dramatically reduce errors all over the flat plane from PBE with this approach. So NE, U, and J is the non-empirical coefficients eliminating these errors. So we've shown that this is a way to mitigate empiricism, and I will skip over the last couple of slides unless someone is interested to know, but we also took a look at what are we actually doing to the density when we do this. And the answer, I guess I will say the punchline, is that in molecules it seems that things like Hubbard U are actually doing much more to localize density away from the metal center onto the ligand than we think about. We usually think about the Hubbard U correction as localizing density onto the metal and away from the ligand, but the problem is actually much more that we need to push it off of the metal and onto the surroundings. This is a little bit more complicated in solids than it is in molecules, but hybrids, when you use a hybrid functional, it is pretty much universally in these systems moving density away from the metal and onto the surrounding atoms, because those surrounding atoms are actually more localized than the metal. And this runs counter to most of the language you hear around DFT+U. But I definitely don't want to run any longer than I have. So I'd just like to conclude. Some of the things that are nice about DFT+U is that it really is simple to interpret, and you should know that DFT+U should never worsen fundamental aspects of our electronic structure. It should never make self-interaction error or electron delocalization error worsen. It should work to recover piecewise linearity, but not necessarily at the computed Hubbard U, because Hubbard U and global curvature, which is how we recover EDE, are related in a weird way. But the thing to worry about with DFT+U is that you're winning at the electron delocalization error, the energetic delocalization error problem, but worsening static correlation error. So when things go wrong, it's either because DFT+U is doing nothing or because it's worsening static correlation error. And there are ways to address both of them, but they're not as widely used yet. There are a lot of things that I didn't talk about that were practical issues to do with, does DFT+U make your lattice parameters too big? Does it make your bonds too long in your materials? That's some of the work we did on V terms. Do you need to balance localization and delocalization? I'd be happy. I think I have a brief discussion with some of you after this. I'd be happy to talk more about any of those things. I'd just like to conclude by acknowledging my group and some of the funding sources. In my group, electronic structure subgroup members who work hard on this are, I had a chance to tell you about some of the work done by Akash Bajaj, Feng Liu, who's just started at Emory Chemistry, as well as former members of my group, including John Paul Janae. And thank you very much for your attention and for all of the material I just ran through, for being patient with that. I'll take any questions now that I missed. And I saw there were some in the chat. I didn't see what was going on in chat.
Thank you very much, Professor Kulik. Thank you very much. So we'll take questions now. Okay, Dr. Prasenjit Ghosh raised his hand. So Prasenjit, please go ahead. Unmute yourself and ask.
Hi, it's a nice talk. Can you please go to slide number 4?
Okay.
Sorry, I have to ask you to go.
Oh, I'm not particularly good at rewinding my slides. Yep.
The next one. Yeah, so what I understood is, not this one, the previous one.
Okay.
Yeah. So I mean in my what I understand, I mean in terms of being less covalent and more ionic, is that in case of ionic systems, I mean the charge density is localized on the ions, while for case of a covalent bond, it's more delocalized in the sense at least it will be more, I mean, spread out between the two atoms that are forming the bond.
Mm-hmm.
So the way I understand DFT+U is that it tends to it acts as a penalty function to localize the electron. That is, either it takes a fully occupied or fully empty state. So I didn't quite understand your comment that a high U value means more covalent and a low U value means more delocalized, or less covalent or more ionic.
So this is exactly the computed linear response Hubbard U. This is not the U needed to get a good property. So if you compute the linear response U, it's the curvature of the energy with respect to occupation variation. That this is telling us that the curvature variation is higher in a covalent bond. It's not telling us what Hubbard U will get us good properties with respect to experiment or anything like that. It's that if you compute that value, what's special about this series of molecules is that they all have exactly the same number of electrons, but I've ordered them for you in a way that I qualitatively refer to chromium fluoride as essentially Cr plus F minus in my head, right? But FeO plus, if you look at it, it has that strong bonding. And so one of the things that's attractive about it is that the linear response U that you compute, this curvature, is a reporter for how covalent or ionic the bond is. So I think that's consistent with, now, what effect is the occupation matrix? What effect is the U penalty going to have? The U penalty is also going to be smaller on a more ionic bond than on the more covalent bond. But if you buy into the world that the linear response U tells you how much correction to have, this is attractive because it tells you you want to apply a larger U for the more covalent system and a smaller U for the more ionic system. I've just shown you in the second half of my talk that I don't totally agree with that, but that is what the linear response U will tell you. If the electrons are more delocalized, the curvature is higher from the PBE functional. That's all this is showing at the bottom, which I think is consistent. It's not inconsistent with what you were asking. No,
I was a bit confused. And I had a second question. So can you comment something on this DFT+U plus this W or V, I've forgotten what they call, where they take this covalency also into account.
Yeah. Yeah. So, so we wrote a paper in 2011 showing that it was helpful for transition metal dioxides. And that's why I said, I think on my last slide, here are some things I didn't talk about. I just don't have any slides on it, right? I think it's one way to think about what is neglected in DFT+U. We have moved much more to the perspective of either the occupation matrix detects what you want to detect or it doesn't. The V is, I think, an approximate way to get back to detecting more things in the occupation matrix. But these other approaches popularized by a range of people, including, say, putting a Hubbard U on the P states of the nearby might be preferable. I think they're all getting at the same thing. That maybe since I don't have slides on this handy, even in my backup, I will bring up the thing I went through kind of awkwardly, which is that so in many cases the U can only see so much because it can only see what's going on the D states, and for sure it will over penalize the localization, and so that's where you end up with these overly long bonds, and once the bonds end up too long, then the properties end up wrong. That was the case we worked on that we found the V was helpful on. But I think in all of those cases, you're almost certainly going to end up in a situation where if you can afford it computationally, the hybrids are attacking the problem better because they're taking a global view on the localization problem.
Okay. Okay.
Other questions?
Hello.
Yeah, go ahead.
Yeah, thank you, Prof. Kulik. The question I have is about the transferability of this Hubbard U. What I mean is, for example, you are studying two systems, for example, Cu2O and Cu2O2, for example. They have in common the copper, and assume to what extent can you keep the same value for that copper when you are studying a given property in both systems, for example, the band gap?
Yeah. So
another question related to that is, assume you are studying two properties for one system, for the same system. It could be band gap or the structure of the constant. I mean the structure, any other structural property. To what extent could you rely on the same Hubbard U? Thank you. I don't know whether I'm clear.
Yeah, I understood both the questions. So there are a couple of interesting issues. So one particular approach I took early in my PhD that I definitely still advocate is awareness of the sensitivity of the property you want to predict. That's actually closely related to what we're showing here, to the Hubbard U applied. And so if you know that the property you want to predict is changing dramatically with a small change in Hubbard U, that means something different than if it changes relatively little. And for instance, we were interested in catalytic properties, and what you would typically find is that using the wrong U by about 1 electron volt, so use a U of 4 when you meant to use a U of 5, would only change the property we were interested in by about 0.1 EV. So compared to the error in the original PBE functional, it's okay often to use a Hubbard U that's off by about 1 EV, and it's not going to dramatically change your properties. Other properties could be more sensitive. I think I just basically made the case that band gaps shouldn't shift. I guess band gaps shouldn't shift more than 0.25 EV per EV of U. So similar things in play. I think the challenge is when the two properties you mentioned are additive. So I will get back to your first question in a moment. the properties are additive. So if you change the lattice parameter because you use a U and that U is too big for the lattice parameter, then the band gap evaluated at that overly expanded cell can be wrong because also the structure is wrong. So we know that large U values, that using a lower U for structure is usually good because of these challenges of over penalizing hybridization in the bond. And so I think it's not surprising that many people report seeing a different U give different properties well. And you can think of that as the limitations of the functional form. There's only so much that U over 2n times 1 minus n can do for a system. Now, similarly, what I think is transferable about Hubbard U values is the electron configuration the same? So back to the copper question, is the electron configuration the same? Is the hybridization the same? That is one piece of it. The piece that I swept under the rug, or that that is discussed in one of the appendices of one of my papers and someone else has written a full paper on, is that if you were to look at computed linear response used, those can be sensitive to the occupations used. So where does the projection get evaluated from? Which pseudo potential did you use? I think you should worry more about, are you extracting Hubbard U values recommended in the literature from someone who used a different pseudo potential than you did, and that can be, I think, even a bigger source of disagreement. That being said, if the hybridization environment is the same, if the thing you want to fix is the same, if the occupation matrices are transferable, and this is usually pretty easy to figure out in organic systems, right? So to use an analogy from organic systems where it's easier for me to say on the fly how this works. If you have an sp3 carbon, then the U parameter for an sp3 carbon should be the same in a new system with sp3 carbon. But if you change to sp2, then the right U should also change. So similar with your copper systems, if the copper d electron configuration or its hybridization is changing dramatically, you would think overall in both of these systems, the Hubbard U should change. However, what I would say is that knowledge of sensitivity of the property you want to predict with Hubbard U should guide you, because for sure, even comparison to a hybrid functional, computing your result at Hubbard U of say 5 eV, 4 eV, and 6 eV, that should all be linearly varying, and you can reconverge your electronic structure at these different Hubbard U values, just changing them slightly, and that will give you the a good central difference approximation to how much Hubbard U is going to change the property you want to predict. That's probably ultimately what I'd advocate, especially if you're just aiming to get a range of properties correct and try to know how much the U is influencing that property prediction.
Okay. Sorry, please. Thank you. Yeah, I have a question. The judiciously modified DFT, how well does it do in predicting band gaps?
So it will exactly recover the delta SCF band gap. The only cases where these types of methods fail is when the U cannot open the gap. So we have one paper where we show we don't open a gap and it's known experimentally the gap should open. And that's because the errors are invisible to the occupation matrix. So the occupation matrix can't detect which states it's supposed to separate, and we're working on changing how the occupation matrices are calculated, and that's more of a general issue. That's a DFT+U issue and a JM-DFT issue, and that relates back to when atomic orbitals aren't the right basis. That might also relate to some of the questions that came up earlier with V, is a lot of times when these things fail, it's not really the DFT+U method, it's that the construction that we project onto the atomic states and the atomic states tell us about the error in the functional, that's what's failing.
Okay. Okay, thanks. Any other questions?
Hello? Hello?
Yep.
Hello, can you hear me?
Yeah, Jonah, go ahead.
Yeah. Thanks a lot, Professor, for your lectures on this. So this is a question I want to ask, because I've been sort of arguing with a friend of mine, in which we are just beginners in this area. We are looking particularly at the performance of GW-based calculations on. We know that this works very well if one looks at SP bonded systems, but thinking at doing GW on D orbitals or F systems with F orbitals or so, it seems as though it doesn't really work well. So we are arguing basically just as students arguing on this area, we are looking at a particular usage of using LDA+U as a starting point for G0 W0. Yeah, but also my argument usually is that the Hubbard correction can result in some cancellation in the self energy. This is more like an assumption that I am making. As such, I think that using G0 W0 on top of LDA+U might not really be the right way to look at this. Yeah, so this is just an argument, and I just want to verify from you. Yeah.
So so there are a couple things in play with G0 W0, and I think the most interesting paper to take a look at, it's sometime in the past 3-4 years, and I think it's from Patrick Rinka's group. But they basically argue that you could compare these, you know, what do you use as your starting electronic structure method before G0 W0, basically he shows that there's still residual errors in the eigenvalues. So this delocalization error, if you look at when GW works, especially in the one-shot method, it's because it recovers this piecewise linearity exactly where you want it to. But you can actually assess the benefit of different starting points for your one-shot GW in terms of after you've applied GW, where are your eigenvalues sitting, and how close is that to piecewise linearity? And so I think your instincts are probably correct in the sense that starting from DFT+U, that's already almost getting you to piecewise linearity, and then applying one-shot GW on top is likely to overcorrect issues. That being said, if you're closer to the right ground state, a small u could be helpful. Ultimately, GW in the one-shot scheme with tuning the original density is not necessarily, it's essentially a series of cancellation of errors. And because it's a perturbative technique, it's going to suffer more from static correlation error. And DFT+U already, as I mentioned, increases the static correlation error. So that's the penalty you're going to pay for doing those two together. But this, I think the Rinka paper was nice. It was a physical review B, probably 2016 or 2017, and they specifically, that delocalization error I spent the middle part of my talk talking about, and the deviation from linearity, they specifically see that there's still essence of that remaining even in one-shot GW calculations, and that you can look at which ones give better band gaps in the context of less of that residual error being there. So that's one of the challenges. And so you can think of the way people are often tuning what they start with when they do the one-shot GW as essentially minimizing in an indirect way that error.
Thank you very much.
Thank you.
Any other questions?
I will look at this paper. Yeah. Okay.
I hope I got the reference right. I have it. If you really can't find it, I have it in my library, so I can, which is on my computer. I don't know why I was pointing behind me. I can email me and I can pull it up if you have trouble finding it.
Okay. Thank you very much.
Okay.
Any other questions?
Yeah.
Okay. So if there are no other questions, then we thank Professor Kulik.
Sorry, sir. Hello?
Yeah, sorry, there's a question. Go ahead.
Sorry, I have a question concerning how to get the optimized value of the U.
Mm-hmm.
Yes, because I know in most calculation, I discovered that as you increase the value of U, the band gap is affected. So at what point will you stop? Will you stop increasing the value of U? That is, how do you get the optimized value of U to give you the right band gap of a new, basically a novel material? So that's the question I have. Thank you.
So if you were studying a finite system, the short answer would be that doing this will give you the what I showed here, which is basically the mismatch of the eigenvalues. I guess the closest to that in the solid state. So this thing on the right here will recover the exact band gap. But if you're talking about just tuning to recover the band gap you want, you know, what we usually say is that a U below 5 to 6 will have linear, and I hinted at this, but I should have had a slide on this, will have linear, any property you predict will have linear dependence with Hubbard U in the first, for moderate U values, say up to 6 eV. So you should know pretty quickly how much your property, say your band gap, is going to shift when you apply the Hubbard U and slowly increase. Now, a challenge that can arise is if you apply a very large U value and that changes your converged electronic structure entirely. That may be something you want, or it may be something you don't want. You'd have to analyze it. People do this in DMRG calculations too. People do this all the time, right? Is that changing the Hubbard U correction can change the converged electronic structure. But that being said, for a given electronic state, Hubbard U values, anecdotally about 6 eV or below, will linearly alter your properties. So you will know if my PB band gap is here, increasing the U by this much, say scanning through in 1 eV increments will tell you how much you can expect your band gap to shift. I think if you're just trying to recover band gaps, there's a couple of different things to think about. There's the Tran Blaha modified Becky Johnson. There's Maria Chan and I were co-workers at MIT at one point. She basically did an approach to think about adding an electron to a system to get a delta SCF-like gap out of solids. And the other thing I would say is that if you're in molecules or if you're in systems where you can identify the deviation or the mismatch in the eigenvalues of the occupied and the unoccupied system, that tells you explicitly how much band gap underestimation you have. That's what we showed here. Basically, once you apply the Hubbard U that gets this piecewise linearity back here at 5 eV, you have exactly the band gap you want. Now, if you're trying to just reproduce an experimental band gap, I think you just want to do a combination of what I said, which is apply a couple of increments of Hubbard U and then see how much your band gap is changing and see if there is a U that will recover the band gap you wanted. Without knowing what regime you're in, I don't know, but a useful thing to note is that Hubbard U will produce linear variation in the property you want to predict up to moderate values of U, and then you may see nonlinear dependence as the electronic structure starts to change. And usually this is where you can run into trouble because if you need to use a U of say 20 eV to recover your band gap, then you're also going to do the things that some of the earlier questions alluded to, which is like maybe you'll mess up the lattice parameter, maybe you'll get another property wrong. So if you need a really large U to increase the band gap, you probably don't want to use DFT+U to recover the band gap. But you can know roughly how you're going to shift the band gap with a couple of, you know, a PBE calculation, a PBE with U equals 2, a PBE with U equals 4, then do a linear fit through them. And you should roughly know the range of band gaps you're going to sample. Now, where should you sit on there? That could be the linear response U. That could be, I know the experimental band gap, so I'm going to fit the U to recover the experimental band gap. It could be, I found this U from the literature. Without seeing the system beforehand, I wouldn't be able to tell you which U you should use. But just to know that you don't need to do U at many, many values in order to know that there's linear dependence in the property you want to predict, like band gap. So you can know roughly what the band gaps you can reach are with the U correction just from a couple of calculations, at least.
Okay, thank you very much. George Manali. George, please.
Thank you. Hello, Prof. This is George from Kenya. I'm just so excited with the word judiciously modified. You said that how did the name come about? The reviewers recommended that.
So I wanted to call it Jello mold DFT because what I thought about was that we have these errors and we wanted to not just put a bowl on top, but we wanted to fill it up like you would a Jello mold. And the reviewer said you can't call it Jello mold DFT, so we called it JM DFT, and it's called a backronym. Basically, it was JM DFT could stand for Jello mold DFT, but we said it stood for judiciously modified DFT, which just means modifying DFT carefully.
Okay, great. Thanks, Prof.